Okay, so in this part we're going to talk about weak acid strong base titration, and in the previous section we talk about strong acid strong base. Now we're going to look at a weak acid and a strong base. Now this is the graph that we're going to be getting, and this one, the dash one, indicate how a strong acid strong base titration curve would look like. Okay, so again, a strong acid has a very low pH. We started around 1, right? And this is the curve, and then we had seen equivalence point at pH 7. Now for a weak acid, of course, it's a weak, because it's weak, its initial pH is going to be a little bit higher than a strong acid pH, where we started with 1. Now in this one, the pH is going to be a little higher, right? Around close to 3. Okay. So this titration is 40 milliliters of 0.1 molar propionic acid, HPR stands for propionic acid, with 0.1 molar sodium hydroxide. Molarity is 1 to 1. So we started with 40 milliliters. So if we draw a little diagram, now give me my pen. Come on. No, not you. Right there. Thank you. So this is your flask, and this is your burette. Okay. So here you have your base sodium hydroxide, and this is your weak acid HPR, propionic acid. Okay. Excuse me. So initially we have only HPR, so we can see nothing of sodium hydroxide has been added yet. pH would be the hydronium ion concentration of HPR, and we learn how to calculate that. Okay, and then as you add base, weak acid is going to react with that. Okay, so HPR going to react with sodium hydroxide plus sodium hydroxide. So it's going to give you water plus sodium propionate, right? So you keep on adding. When you add about 20 milliliters of sodium hydroxide, now half of the HPR has been reacted, right? So half of the HPR has been reacted because you add half of sodium hydroxide, and similarly half of sodium propionate conjugate base also has been made. So at that time, right, HPR, the volume of HPR equals the PR minus propionate. So this is your acid and this is your conjugate base, right? So when you have acid and a conjugate base, sodium propionate, what do we have created at that time? We have created a buffer. Remember, we talked about the buffer and we learned about buffer. Buffers are being made based on the acid and the conjugate base. So when you add sodium hydroxide to generate half of propionate from what we originally started, so you have 20 milliliters of this and you have 20 of that, and it's the same molarity, so you have created a buffer. So we call this region here as a buffer region when you add 20 milliliters of sodium hydroxide. Okay, buffer region. And if you take exactly when you add half of your base, you take the pH, you allocate this 20 milliliters, you locate it, and then you find the pH which correspond to that, and that is going to be the pKa of propionic acid. Okay, now if you do a weak acid strong base titration, you have this slope over here. You take the midpoint, that right here, when you add half of your acid, half of your base, not acid, base, and then when you find the pH of that amount, pH of that position, that is going to be the pKa of the propionic acid. I hope you guys remember the Henderson-Hasselbalch equation, where pH of a solution is pKa plus log concentration of base over concentration of acid. Now base is the conjugate base, A is the acid. Now at this point where we found over here concentration of base and concentration of acid are equal, right? Because the same volume has been added, same molarity. So since this become 0 log 1, and then pH of that solution equals pKa of the acid. So that's what you are seeing over here. pKa is equal to the propionic acid, which is 4.89. Okay. Now we're going to be doing one experiment similar to that, acid-base titration. You're going to be doing a weak acid and a strong base titration. So you can find out the pH of the buffer region and from the pKa from therein. And also if you do a strong acid, weak base titration, it's the same thing. You can find out the pKb by looking at the slope of the base during strong acid, weak base titration. Okay, so that's about the buffer region and how to find the pKa. And then you keep on adding your base. And then you add 40 milliliters of your base. At that time, what's going to happen? You see the equivalence point and the end point. So at the equivalence point is not exactly at pH 7. It is going to be at a pH higher than that. 8.80 is the equivalence point. Why do we get a pH higher than 7 when you do a weak acid strong base titration? Let's look at that, the reason behind that. I'm going to go ahead and erase all the pen markings. Remember what happened. Now you have a weak acid HPr plus your sodium hydroxide, and at the end point what you're going to have is water plus the salt NaPr, sodium propionate. When you reach the equivalence point, that is what you have. Number of moles of hydrogen coming from the acid done reacting with the number of moles of hydroxide added. Now at this point we have water and a salt, right? Now we're going to see how this salt going to react with water or addition of more hydroxide ions. Okay, so let's remember we learn about if you have a salt. If you have a salt, sodium propionate, we learned about earlier, now salt will dissociate into ions completely, Na plus plus Pr minus. Now we're going to see this is a cation coming from a strong base, so it's not going to react with water. Only propionate anion, which is a anion of a weak acid, going to react with water. How is it going to react with water? It's going to give you HPr and add hydroxide ions to the solution, right? So since it adds hydroxide ions to the solution, at the equivalence point the solution is going to be basic. Equivalence point will occur at a basic pH. Okay, as soon as you have made a propionate anion, it's going to react with water and then it's going to make a basic solution, hydroxide. So the equivalence point will occur at a pH greater than pH 7, 8.80 at the equivalence point. Okay, and then when you keep on adding a little bit more hydroxide, it's going to follow the same pattern as a strong acid strong base titration, and then you will see that it follows the same path. But initial part is different because we are working with a weak acid and a strong base. Okay, all right. Okay, let's see how can we calculate the pH during a weak acid strong base titration. How to calculate the initial pH, how to calculate the pH at the equivalence point, and how to calculate the pH after the equivalence point. So initial pH will be given by the acid. Let's say you have, since it's been used HA plus water, it's going to give you hydronium ion H3O plus A minus. Remember we did the ice table initial amount and then the X amount like that. Let's say if this is going to be HA initially, and then hydronium ion, let's say if this is X, and this is initially, you can call it as HA, and then HA minus X we said that we can consider as HA at the equilibrium. So Ka was given by X squared over HA, right? X squared again can be written as, since it's hydronium ion concentration, H3O plus squared over Ka, no, over HA, and then if you want to find out the hydronium ion concentration, H3O plus going to be Ka HA, and get the square root of that, right? HA initial amount. That is what you are seeing over here. Ka going to be hydronium ion concentration times A minus over HA. So both of these are going to be the same amount at the equilibrium. So you can be considered as hydronium raised to the power 2. So the hydronium ion concentration would be square root of Ka times HA initial. Right? Same thing that we derived over here. And then the pH would be negative log of hydronium ions. That is the initial pH. We have learned this in our previous lecture, chapter 18. And then if you want to find out the pH before the equivalence point, what do? So you can use the Henderson-Hasselbalch equation. Again, the hydronium ion concentration going to be Ka times HA over A minus. Hydronium ion concentration would be again Ka times HA over A minus, this part right here, right? So Ka, we can consider this part also here too. So the hydronium ion is going to be Ka times the concentration of HA over A minus, right? Hydronium ions. And then if you convert it to Henderson-Hasselbalch equation, taking the log of both sides, pH equals pKa plus log base over acid. So pretty much if you know the concentration of the base and the concentration of the acid and the pKa of the weak acid, you can find out the pH before the equivalence point by using this Henderson-Hasselbalch equation. Okay. And then the pH at the equivalence point. How do we find the pH at the equivalence point? So this is what happened at the equivalence point. Just like I explained during the titration in a previous slide, your propionate ion is what we used in our in my previous explanation. So let's say A minus, similar to propionate anion, react with water, giving you acid and hydroxide ion. So this is what happens at the equivalence point. That's why we have a equivalence point a little bit higher pH than pH 7. So then the hydroxide ion concentration would be, again, if you write Kb for this one, how this came along, okay? So if you write a Kb for this equation, Kb would be Ha times OH minus over A minus for this one when you write Kb. So then the hydroxide going to be hydroxide and HA, they are going to be the same amount like your X amount, right? So then the hydroxide going to be Kb times A minus, and you take the square root of that, right? Kb times A minus. That's what you have over here, since both of these are same. These two are the same if you consider them as your X. Okay. So where Kb times A minus. Now how do we find the A minus, this amount? How do you find that? Remember, from a titration, we have the initial number of moles of HA, which is going to be your acid. If it is propionic acid, what is the number of moles of acid that we have added? We can find out from the molarity and the volume. You can find the number of moles. Excuse me. Now, but at this time, you have added base also to get to the end point. Now, this many number of moles are present in this many milliliters of volume. Your initial volume of the acid plus the base you added to reach the equivalence point. So, you take the whole volume. And then when you divide number of moles of HA initial, divide by the volume, that will give you the amount of A minus conjugate base present. Okay, and we also know this equation where Ka times Kb equals Kw. So Kb would be Kw over Ka. Okay, so we can rearrange it to give you this equation. So let me show you how we get this equation. So basically we know hydronium ions H3O plus times hydroxide equals Kw, right? So the hydroxide ions are equals Kw over H3O plus, right? H3O plus. And in other word, H3O plus equals, should have done this, Kw over hydroxide ions both ways, right? Hydroxide ions. So hydronium ions are equal Kw over hydroxide. So we put the Kw here, and then for the hydroxide ion, it is this amount. So you divide it by here. Got it? Hydronium ion is Kw over hydroxide. So Kw is right there at your as your numerator, and then hydroxide ion, this amount, which is Kb times A minus square root, going to be your hydroxide. That will give you hydronium ion concentration after the at the equivalence point. At the equivalence point. And how to calculate the A minus is given with this equation. Once you know the hydronium ions, pH would be negative log of hydronium ions. That is how you would calculate the pH at the equivalence point in a weak acid strong base titration. Now, how do you calculate the pH beyond the equivalence point? Again, after the equivalence point, we have added more of hydroxide ions. So we want to find out the molarity of the hydroxide ions added. Moles hydroxide, and you divide it by the moles hydroxide added in excess, you divide it by the volume of the hydroxide plus the acid, because now this hydroxide is in the total volume of your acid plus the added base. That will give you the concentration of hydroxide, and again hydronium ion can be found Kw over hydroxide. From there you can find out the pH of the solution. Okay. It looks little longer calculation, but if you try to understand it step by step, it makes sense. Again, the excess moles of hydroxide we find by getting the total number of moles of hydroxide, and you subtract it with number of moles of not the hydrochloric acid, but the weak acid present at the beginning. That's how you calculate the number of moles of hydroxide is in excess. Okay, so that is all given in equation form. Let's do actual calculation and see how can we find out these values, right? That will make more sense to you now. Calculate the pH during the titration of 40 milliliters of 0.1 molar propanoic acid, Ka given after adding the following volumes: 0.1 molar sodium hydroxide 0 milliliters and 0.1 molar sodium hydroxide 30 milliliters. Okay, so we can calculate the initial pH. 0 milliliters meaning initial pH. Again, this is a weak acid. So we can find out the hydronium ion concentration, square root of Ka times HPr. I showed you how we get this equation. So the Ka is given 1.3 into 10 to the negative 5, and then we started with initial amount 0.1. Get the square root of that. That will give you hydronium ion and then the pH. And when you add 30 milliliters of 0.1 molar sodium hydroxide, first we need to find out the initial amount of acid, which is again the volume times the molarity. Volume we added 40 milliliters, 0.04 liters, times the molarity 0.1, so number of moles. Now we added 30 milliliters sodium hydroxide, so we want to find out amount of sodium hydroxide added, 0.03 times 0.1, 3 into 10 to the negative 3. That's the number of moles of sodium hydroxide. So each mole of hydroxide react to form 1 mole of propionate. So we can construct a ICE table. Initially we have propionic acid 4 into 10 to the negative 3. Initial hydroxide amount, this amount that we calculated. Nothing has been formed yet. And then since the hydroxide is less amount compared to HPr, this all will going to react with propionic acid. So the change is going to be the amount of hydroxide ion. Same thing for this one. And then since the ratio is 1 to 1, if you react this much with HPr, you are going to make the same amount of propionate plus 0.003. Right? So the final going to be the difference of this 0.004 minus 0.003, 0.001. Hydroxide will not be there, it all be reacted, and then the propionate would be this much made. Now we know equilibrium amount of propionic acid as well as propionate. So to calculating a pKa, because we were given the pKa would be negative log of Ka, and we can use that information putting into the Henderson-Hasselbalch equation. pH equals pKa plus log base concentration over acid concentration at the equilibrium position, equilibrium point, right? Equilibrium concentration, sorry. Okay. So then the pH, what we want to find out is the pH, and then we found the pKa by using the Ka, and the concentration of base Pr minus we found 0.003, and then the concentration of the acid at that time is 0.001. So this will give us the pH of the solution. Okay. Okay. It is the same way that you're going to find out if you reach pH beyond the equivalence point. Okay. Okay, and here's an example of a graph where when you do a weak base strong acid titration. So if the base is weak, it's not going to start at 12, it's going to be less than 12 pH. This is ammonia around 11. And then just like we do as weak acid strong base titration, as we add hydrochloric acid or acid into this, you can see the pH drops. And there comes a point where ammonia, so this is ammonia hydroxide solution, ammonia solution which is ammonium hydroxide. At this point, ammonia become similar to ammonium ion concentration, that is the buffer region. Okay, and then if you take the midpoint of the buffer region, you can find out the pKa of ammonium ion, 9.25. pH is equal to pKa of the ammonium ions. And then pH drops and reach the equivalence point. Equivalent point will be reached below 7, because at this point what you have is ammonia becoming ammonium hydroxide. Ammonia is the base, ammonium hydroxide is the conjugate acid. So ammonia NH4, okay, before that, ammonia react with HCl will give you ammonium chloride NH4 plus ions it's going to break into ammonium ions and chloride ions, and then the ammonium ions going to react with water, giving you ammonia NH3 and H3O plus hydronium ions. So right after the equivalence point, since you are creating ammonium chloride, ammonium ion react with water to give you hydronium ion, make it acidic medium. Okay, chloride will not react because it's an anion of a strong acid. So that's why pH would be less than pH 7, because you are generating hydronium ions. So the end point is around 5.27. And then as you keep on adding hydrochloric acid, pH decreases and follows this pattern. Okay, so this is a weak base strong acid titration. We'll talk about acid base indicators in the next session.